So welcome. There's going to be two talks about 15 minutes each, and feel free to ask questions at any point or at the end. I'm going to start off by talking about mutation testing, mutation analysis, but first of all I want to just talk about myself, which I like doing best. So I want to just talk a bit about my background. So I'm actually somebody who used to work in industry, who made the move into academia about 10 years ago. So I started off in the beautiful city of London as a developer working on database systems. I then moved to the beautiful city of Boston, where I was a project manager, and I worked at startups and some healthcare companies around financial systems. For some reason I then decided I'd had enough of that and moved to academia in the beautiful city of York, where I was a PhD student working on something called search-based software testing, which would be normally the subject I would talk about most gladly. But I know some of you have seen me talk about that before at the Karlskrona test gathering I was talking about, so I'm going to talk about mutation testing today. And now I'm in the beautiful city of Karlskrona as an assistant professor, and my areas both in terms of teaching and in terms of research is around software testing. So why talk to you about mutation testing, mutation analysis? It's not my main research topic, so why did I choose this? Well, partly because it's not a topic which is widely known outside of academia. And this became obvious to me at one of the Karlskrona test gatherings when a few people mentioned mutation testing, and it appeared that many people hadn't heard of it and didn't know what it was. And this is typical of a lot of academic techniques, and it's a real challenge to get what look like good academic techniques into use in industry, which is one of the reasons I want to talk about it today. And also, it's a very mature technique. It's been around for about 30 years. And there's good evidence that it does work. I'm not going to say it's perfect, there are challenges, and I'm going to talk about those. But there's really good evidence that it does work. And it has some tool support, so it doesn't require you to talk to academics, which is always a bonus. And it's a topic we will cover on some of the comp testing courses as well, so I wanted to give you a flavour of some of the things we're going to cover. So mutation testing is actually really simple in how it works. So say you're testing a program, and usually mutation testing is applied at the unit level, but you can apply it also at an integration level and larger levels. But say we've got a program. We take the original program, we make a small syntactical change. So we actually take the source code and make a small change so that the program still compiles, but it's slightly different. And then what we want to do is find test data which you can apply to both programs, but the output from your mutant program is different from your original program. And in this case, I'm not going to talk about what the program is, but if we enter 8 and 20 as our inputs, we get an output of 7 from the original program and 9 from the mutant program. So we found, if you imagine the mutation is like a very simple bug, a very simple fault in that program, we found it by some test data. So the logic is that this test data of 8 and 20 is actually a good test case because it's found a very simple fault. So what we say at that point is the terminology is that we've killed the mutant. We found test data which identifies that the mutant is a mutant, it's not what it should be, and therefore kills it. So an example maybe this is a really trivial program taking 2 inputs, and there's lots of ways we could mutate it. So for example, in the second line down we could change on the variables from A to B. And that will still compile, but there's going to be some test cases for which it's going to give a different output. Similarly, we could take this comparison operator here, so instead of B is greater than 19, say B is greater or equal to 19. And another one we could make is, instead of saying H is A minus 1, you could say H is the absolute value of A minus 1. And these are some of the common mutation changes which are made and have been shown to be quite good. But I hope you're thinking at this point, hang on, I know from my experience of testing, these aren't the kind of bugs which you find. You don't typically find bugs which are just, they've made one tiny mistake, basically. Bugs are much more complex than that. Faults are much more complex. Well, the nice thing is that mutation testing has some theory and empirical evidence to back this up. And the evidence has started in about 87 and there's a lot of evidence been gathered since, which says, okay, yes, these mutations, you can think of them as really simple seeded faults. But they're not realistic. They're not realistic of the faults that programmers usually make. But there's a nice relationship between real-world faults and these really simple mutations. And it's called the coupling effect. And there's been a lot of evidence which says if you have test data which can find these really simple faults, you'll also find the really complex faults which happen in real life. And people have done a lot of studies and shown this. And that's nice because it says, for example, say we have a new program. We don't have any bug history, so we can't actually seed real-life faults. But what we can do is this technique, which is just to make really simple small changes. And the coupling effect says that if we've got good test data which finds these really simple faults, it'll also find the more complex faults as well. And that's the whole premise of mutation testing. So the process you would go through for mutation testing is you would take your original program, you would make a number of these mutants, so these really small simple changes to introduce simple faults. And then you just create test data which kills each of the mutants. Now I'm going to skip over the fact that's non-trivial. Okay, finding test data is non-trivial, and there's some other research which can help find that test data. But the idea is, just like you might construct a test set, a test suite for coverage, so you cover all the branches in the code, this is kind of the same thing, but it's saying instead of branches, cover all these mutants, i.e. kill them by finding test data which shows they give a different output from the original program. And that's the whole premise of mutation testing, which has been found to be really effective. So one of the reasons it's particularly effective is an argument that it's stronger than structural coverage. So if you're familiar with, for example, branch coverage or line coverage, well, for a mutant to be found, for a mutant to be killed, i.e. we give it inputs and then we run it and it gives a different output from what we expect, a number of things have got to happen. First of all, we've got to reach the point at which the mutant is. So in this case, we have the mutation is inside a branch. So we've kind of got to do branch coverage to even get to the mutant. And then we've got to give it interesting data, which gives a different output from what we would normally get. So there's more conditions than just for branch coverage, especially if you imagine you're making mutations all over the code. Typically you make a lot of mutations. So there's a lot of evidence that it's stronger than structural coverage and it can find more faults than structural coverage in real life. The downside is that you typically need many more test cases to do this, and obviously that's a big issue. And I'm going to talk about how you can perhaps minimize this. But another challenge, and this is maybe the reason why it's not really used as widely as it could be, is how do you decide what mutations to make? There's a lot of possibilities. You can change variables, you can change numbers, you can change operators, and if you do that on even a simple program, you can get thousands of mutants. And if you're going to create test cases which kill thousands of mutants, it's probably going to be thousands of lines long, which for a simple bit of code like this, obviously you don't want to do. The cost is just too much for finding real faults. So the other nice piece of research which has been going on for about 20 years is, well, what changes should you make? And it turns out that a lot of changes you could make, like for example, I could say change that 19 to a 20. They're nice, they are simple mutants, but in fact there's other changes I could make which result in fewer mutants, which are effectively equivalent. And for example, if I do this relation operator replacement where I just change one relation operator, in this case b is greater than 19 to b is greater than or equal to 19, if I make those changes, it will guarantee that the other changes, like for example changing 19 to something else, will also be found. So just like, for example, different forms of structural coverage, like for example if you do path coverage, it will mean that you definitely get branch coverage as part of path coverage. The same is true of some of these mutation operators, which are how you make mutants, that some of them imply that other mutants will automatically be found, so you don't need to do the other ones. So you can kind of cut down which mutations you make and still have that coupling effect which you want, which is making some small, simple mutations results in finding the complex bugs eventually. And a great deal of work has gone into, for different languages, what are the right operators to do. And that's going to reduce the number of mutants you have, and therefore the size of your test sets.
So basically it's better to change the logic than to change the data, because then you get a greater coverage of the mutants.
And it turns out, and there's no theoretical reason necessarily why this is the case, but people have done experiments. And to be honest, when I was researching this talk, when I was giving examples of mutants, my first instinct was to change the 19 to a 20, like you're doing kind of boundary value testing, but kind of in the code. And then I read up on what the right operators were to use for this bit of Java code. And they said, no, actually, experiments show that it's better to use this replacement operator where you change that. So, and it just reduces the set. There's actually a piece of work, a really interesting piece of work a couple of years ago, where they said, in fact, you can get away with one mutation operator in some circumstances, which is just to delete a line of code. And it turns out that if that's all you do, you get pretty good results. And obviously, you haven't got that many lines in something like this, so deleting the lines of code results in quite a small test set, which is still very effective. Not a lot of people believe that result. It sounds too good to be true, but there's a lot of research going in that direction, going, can we actually get away with a very small set of different mutants and still find real-world bugs with the test sets we create? The other problem is, in practice, it sometimes doesn't matter, but what we want from a mutant is that we can find test cases which give different outputs. But you can make some changes to code where it's the same as the original program. You can't always guarantee that a mutant will result in a program which behaves differently from the original. So in this case, I changed the variable A to H, but because I set H to A 2 lines above, it's the same program. I will never find test data which gives a different output. So the trouble is, if you can't identify equivalent mutants, you can spend a long time trying to find test data which kills that mutant, but it's never can be killed. And there's techniques, which I'm not going to spend time going into, where you can guess when you've got an equivalent mutant and not spend a lot of time trying to find test data for it. But this is also one of the challenges of mutation testing. Now, the title of the talk was actually about testing your tests, and to do this, what I meant was you can use something like mutation testing to look at existing test sets and see how good they are. So on the premise that if you create these small, simple forks, mutants in your code, well, you can take existing test sets and see how good they are. So you start off with a test set, you then create some mutants, and you see how many of those mutants are killed by the existing test set. So for example, in this case, I kill 3 out of 4, and then you can give it a score, which is the proportion of mutants you kill, 75% in this case. So, I mean, typically you have more than 4 mutants, you have perhaps hundreds of mutants, and I think a lot of the times test cases are bigger than 4 test cases. But the idea is that if you want to have some indication of how good your existing test sets are, or you want to compare 2 different techniques, this is one way you can do it using mutation score. So you might use something like coverage currently to kind of assess how good your test sets are. The argument that people who use mutation analysis would make is that there's a lot of research which says coverage isn't always great at predicting the faults you will find. But because of this coupling effect between small simple faults and the real life faults, mutation score is a better indicator of how many bugs you will find in real life. And then the final technique I want to talk about is to use this to actually reduce the size of your test sets. So one approach you can do for this is kind of like mutation analysis, is have your test set and you create some mutants and you go through your test set one by one, test case by test case. So say the first test case finds 2 mutants, it kills 2 mutants. Well, I'm going to keep that in my test set. Okay. Now I look at the next one, and it might kill, perhaps it kills one of those 2 mutants, but it doesn't kill any new ones. So why have I got it in my test set? I could remove it if I wanted to, and I'll still kill the mutants. And then, same with test case 3, it kills no extra mutants, so I'm going to remove it. Test case 4, perhaps finds one, so I'm going to keep that one. Test case 5 finds no extra. Test case 6 finds that last one. So I've reduced my test set down from 6 to 3. And on the basis that I want a test set which kills all the mutants, because if I kill a lot of mutants, I'm likely to find real bugs. On the idea is that some of those test cases in between weren't finding any new mutants, so there's not much point running them. So this is not, obviously this can only be used in certain cases, but say you're doing manual testing and you've got to check the output manually against what it should be. Well, this reduces the number of test cases you need to check. And of course, this is probably a typical case when you've got integration testing. You might, regression testing, you might build up your regression test suite over time. This is one way to look at the regression test suite and say, can we actually remove some of the tests now? Do some of the tests effectively do the same thing? And looking at which mutants it kills is one way to do that. Finally, just the last couple of slides, I want to talk about, this is kind of some research I'm involved in at the moment, but mutants don't have to be applied to program code. So in a lot of cases, you might have programs which, for example, take XML, or they may take particular file formats in. And often you have a specification which tells you what is a correct input. So for example of XML, you can use something called XML schema definition. In the case of file formats, you might have DNF grammars or something similar, or just a written specification of what those file formats are or those protocols you're using. And this tells you effectively what is valid data. But sometimes you want to test a program with data which isn't valid for robustness. And one way you can do that, if you imagine that you have this space and everything in the circle is what, for example, that XML schema definition or the grammar or even the written specification says is the right input, that's fine. You can run it with test data which is valid according to that specification. But sometimes some interesting things happen just on the boundaries, things which are just invalid. So for example, when people are testing security, they send data which is just invalid, just to see, because it gets through some initial checks, but it might cause some security issues like buffer overflows and so on. And one way, when you have something like XML schema or BNF grammar, one way to do that is to make tiny mutations in that grammar and then take inputs which satisfy that mutated grammar, because it's going to be just outside the valid region. And this is something I'm looking at the moment, and we found it pretty good for some programs, just for testing robustness. Do programs detect well that they're being given slightly invalid inputs and report in an effective way? And we did that by effectively mutating the specification of what is a valid input. So, to summarise, mutation testing, mutation analysis is built on this interesting premise that tests that kill mutants, small, simple, arguably unrealistic faults, also detect real-life faults, which are typically much more complex. And if that premise holds true, and there's evidence that it does in a lot of cases, there's a number of techniques you can do using this concept of making mutants with very small changes. One is mutation testing, so actually create your test sets to kill mutants. The other is mutation analysis, which is assessing the fault detecting ability of existing test suites by seeing how many mutants are killed. And then test suite reduction, effectively use mutants to tell when test cases are effectively similar, they're going to kill the same mutants. So if you're short of time, short of budget, short of people, why not remove the ones which seem to be doing similar things? Then finally, I said there was tool support. So I mentioned 3 tools. Full disclosure, I don't use any of these. I use a slightly different tool to the language I'm working in. But these are produced by my colleagues, some colleagues in other universities. The first one is from Professor Jeff Offert, who basically is the big name in mutation testing. And this is a tool which is widely used by people, at least in academia, for creating mutants. And the other 2 is for Java and then for C. So that's it. Thank you for your attention.